All right, we're going to continue with section 14.9. So at times, we will be given a surface S and have to find its vector function. R of UV. So let's put an asterisk right here. I'm going to give some different scenarios, different ways we can find that vector function. So in the case where S is given as a graph of a function of X and Y, that is the form X comma Y comma Z equals F of X, Y. A very simple parameterization is X equals X, Y equals Y, Z equals F of X, Y, where here our parameters are X and Y, and the vector function is R of X, Y equals X comma Y comma F of X, Y. All right, so just like we have a favorite trig identity, this is going to be our favorite parameterization. It won't work 90% of the time, but we'll go for it. So if we see that we're given, and the way you can determine whether you can use this or not is whatever function that you're given, or whatever description your surface you're given. If you can solve that for Z, then you know you can use this parameterization, because your description, your surface is usually going to be given in terms of X, Y, and Z. If you can isolate Z, you can use this parameterization. So that means if there's a Z squared in the equation you're given, you cannot isolate Z, because that's going to give you a plus or minus. You have to be able to isolate Z as a function, as a single function of X and Y. Now, similarly, there's a parameterization that's like, there are two parameterizations that are like this. If you can solve for Y in your equation, or if you can solve for X in your equation. So we'll look at an example. But when you see a surface and it's given in terms of X, Y, and Z, some equation with X, Y, and Z in there, your first approach should be, can I solve this equation for X, or can I solve it for Y, or can I solve it for Z? If you can solve it for Z, you use this as your parameterization. If you can solve it for Y, it would be X equals X, Y equals some function of X and Z equals Z. If you can solve for X, then your parameterization would be Y equals Y, Z equals Z, X equals a function of Y and Z, and your parameters are Y and Z. So this would be this is always my go-to. Can I solve for X, Y, and Z in my equation? Now, probably 90% of the time you can't, but it's nice when you can because then you quickly have your parameterization. So let's look at an example of this. We'll do number 6 on page 984. So page 984, number 6. Says in exercises 5 through 10, find a parameterization of the surface sigma. Sigma is the plane 2x plus 3y plus 2z equals 5. 2x plus 2y plus, 2x plus 3y. 2x plus 3y plus 2z equals 5. So when I see something like this, I say, okay, can I solve for z? Actually, I can solve for z, I can solve for x, I can solve for y. So just since we already have it up there for if we can solve for z, I'm going to solve for a different variable just so you see what the parameterization is if you solve for another variable. So it doesn't matter which one you do. If you solve for z, then you would use this up here. Whatever you get for your z, when you solve for z, you'll put that right there. I'm going to solve for x. So if I solve this for x, I'm going to get 5 minus 3y minus 3z over 2. So x equals 5 minus 3y minus 2z over 2. So now, to parameterize this, I'm just going to let y be y, z be z, and x be equal to this thing. So y equals y, z equals z. So my parameters here are y and z. And if we want to write out our vector function, r of y comma z equals, what is x? X is that thing. So when you write out your vector function, just make sure that there are 2 parameters in there. Well, you see 2 there, but make sure there are only 2 variables swimming around on this right-hand side. If you have 3 variables swimming around on the right-hand side, you know you've done something wrong. So our first component is this 5 minus 3y minus 2z over 2, then y, and then z. And that is the vector function for that plane. Now, for this parameterization, as well as the one that we saw in number 4 in the previous video, no restrictions were given for our parameters. So this says y and z are going to take on every value, and this thing will trace out a plane. This vector will trace out an entire plane. In our last problem, the number 4, we had a u and v in there, and the u and v that in there didn't have any restrictions on them. They would take on every value, and they would trace out a sphere. Now, they would trace out the same sphere over and over and over and over and over again, but they would just trace out a sphere. This is only going to trace out that plane one time, though, even though there are no restrictions on x, y, and z. All right, so this is the ideal scenario. That is rarely the case. So what do we do in the instance where we can't isolate any of the variables in our equation, or we're not given an equation like this? And this is the one instance where I sketched that picture, capital R, in the previous video. This right here is the one instance where your region R, your domain for your parameters, actually is in your picture. It's the region that's directly below that surface right there. But that's not something you need to be necessarily concerned about, though, so don't worry too much about that. All right, so now, most scenarios where S is given, and we must find R. require a bit of ingenuity. Versus having a general clear-cut approach. And so we'll look at another example where we're going to have to do something a little bit different than what we did here. All right, so let's look at number 8 on page 984. So number 8 says, in exercises 5 through 10, find a parameterization of the surface sigma. And it says sigma is the elliptic cylinder, y squared over 4. Number 8, sorry. Y squared over 4 plus z squared over 9 equals 16. So here, when we see something squared plus something else squared, oftentimes we want to think of our favorite trig identity, cosine squared theta plus sine squared theta equals 1. So if we use that, or think of this kind of like being an ellipse, well, it's an ellipsoid, but it being, it's an elliptic cylinder. But if we project it if we project this thing into the XY plane, or actually not for us, not XY in this scenario, we have Y and Z, into the YZ plane, then we would just have an ellipse, which is just a deformed circle. So if we use that rationale and say I decide I'm gonna do a change of variable here and 1 right there, then we can rewrite this as y squared over 4 plus z squared over 9 equals 16, which equals, from our favorite trig identity, 4 cosine theta squared plus 4 sine theta squared. So now all I've done is rewritten the number 16 like this. So now that tells me that I would want to let y over 2 be equal to 4 cosine theta, and let z over 3 be equal to 4 sine theta. So we're going to let y over 2 be equal to 4 cosine theta, and z over 3 be equal to 4 sine theta. All right, so we now can quickly see what y and z are going to be equal to. The only thing we're missing is x. But notice, when I solve this for y and I solve this for z, we'll only have one parameter, theta, in there. So x, we need to talk about what x does, but keep in mind that this is a cylinder along the x-axis. So we can just let x vary, and it will take this circle and it will drag that circle, or this ellipse, and it'll drag that ellipse along the x-axis. So we're going to let x just be x. And now we have a parameterization, x equals x, y equals 8 cosine theta, z equals 12 sine theta. And now we see our parameters are x and theta. And now in this scenario, you could put bounds on theta if you wanted to, but this is not necessary to put bounds on theta. You could say theta varies between 0 and 2 pi. It would have to be something that at least has a length of 2 pi, whatever your bounds are that you're going to put on theta. And then if we wanted to write out the vector function, it will be r of x comma theta, our two parameters, equals x comma a cosine theta comma 12 sine theta. And that's how we would parameterize that. All right, so I'll stop this video here and then we'll continue 14.9 in our next video.